Hey, good morning. And doing this on a beautiful sunny day. I'm hoping for a great weekend. The nice weather is certainly important, and hope that you're enjoying yourself and not too bored with the routine of our lives right now. In this video and in this week, we're going to focus on how thunderstorms and lightning form. I mean, we've seen thunderstorms, the most common type of storm on Earth, and we're going to talk about their formation, lightning, and what we know about its formation, and finally thunder and what we know about it. And so these are some pretty common weather events that often are severe weather and lead to a lot of hassle for a lot of people. Let's get started with talking about um, where we find um, thunderstorms. If you look here in this map, you can see that, wow, look at the southeast United States, especially Florida. Look at Florida, 100 thunderstorms a year. Up here in Wisconsin, between 35 and 45, probably for us in the south central region. Notice the Great Plains and the southeast have a lot, but by far Florida and the southeast the most. Look at California, hardly any thunderstorms, and even Alaska. That's just not a weather phenomenon that they have out there. Interesting. Thunderstorms are a storm that generates lightning and thunder, plain and simple. They have very gusty wind as the wind pushes down and makes a wave front, and heavy rain and often hail. On any given time, they're common. On Earth, 2,000 thunderstorms are occurring probably right now. That means 45,000 a day, almost 16 million thunderstorms a year. And that's just an amazing thing. You think it's just a very common thing overall on the Earth. They can form individually or as part of a squall line along a cold front. We'll talk about that. They need some certain conditions in order to start. When they do happen, they generally fall through into three stages: the cumulus stage, the mature stage, and the dissipating stage. So that's the sequence. This sequence can take anywhere from 4 to 12 hours to 16 hours sometimes for this to happen. They can last longer if there's a cold front pushing them. In the cumulus stage, it's those puffy clouds that we see, and what we really need is a lot of instability. We need air, hot, we need warm, moist air that rises and forms a cumulus cloud. But the instability means that it'll continue to rise. So these clouds will get up to 30,000 feet tall, 40,000 feet tall, 50,000 feet tall. Once they're mature, they have a lot of wind drafts and updrafts and downdrafts. And so what they have is a cloud that has cool, dry air entering, going up and going down and going back up. And what that does is churn up all the water and allows them to produce a lot of rain and also generate lightning and thunder. Once they run out of energy for that lift, they start to dissipate. Mostly it's the downdrafts taking over instead of the updrafts. The downdrafts will push everything down. There's not a lot of energy lifting things up anymore, and that'll really slow it down. Once that happens, the storm will start to slow down. You can read through and pay attention to these details. Here's a cold front. And when the cold front comes through, you can see what it does is it literally is like a plow. It'll push up the air. And so that's a really common thing. In cold fronts, we often get squall lines of thunderstorms. You know, basically a long line of thunderstorms that'll push through. And if it moves from west to east, we'll see the storm move along. Here's the cumulus phase. Again, pretty short, what we can think of as standard cloud, but look at the updrafts. Notice the updrafts tend to be on one side and the downdrafts on another. But basically, once we get to the mature stage, we're talking a cloud that's 10, 20, 30,000 feet tall. I mean, that's 4 or 5 miles tall. That's a huge cloud. They're characterized by having anvils on the top. And of course, as soon as the updrafts and the lift leaves, it'll start to dissipate. It'll rain out a little bit, but that's how it'll go. This is probably the most important type of thunderstorm. It's called a supercell thunderstorm. Supercell thunderstorms are a special kind. They can persist for hours, again, 8 to 15 hours, but they are characterized by an overshooting top, an anvil shape. If you can see it, it's flat towards the top. This is usually the top of the troposphere where it comes out. Here's that big cumulonimbus. You can see that they'll have some trailing clouds behind them, but this wall cloud will move in, and right below it will be a big push of air. On the southeast corner, you might get enough of a hook that'll lead to tornadoes. As a matter of fact, supercells are responsible for all the significant tornadoes that occur, anything 3, 4, and a 5 and above. They're also responsible for most of the hailstones, larger than golf ball size. The updrafts in this thing can be 100 miles an hour, with the air rushing up over faster than the speed of a car up towards the top of the atmosphere. And when it comes bursting, pushing down, that outburst or that outflow also can be over 100 miles an hour. These are big storms, characterized in the plains and what we would call Tornado Alley. Lightning. Basically, when you think about all that air moving up and down and the water moving up and down, there's a lot of energy inside the cloud. That excess energy is often released as electricity called lightning. And basically, whenever you have that rapid heating of air surrounding the lightning, it produces a loud clap of thunder. This results in rapidly expanding air. We'll talk a little bit more about that. Check out how hot it can be. Lightning can be 54,000 degrees Fahrenheit. 5 times hotter than the sun, that instant. It's instantaneous, it's very quick. It's not very thick. Actually, lightning is probably about the size of a soda can or even smaller as far as diameter, how big it is. But lightning kills more people than tornadoes and hurricanes combined because it's just so common. Look, 4 million times a day on Earth, there's lightning strikes. It's like we live in an electrical planet where these 4 million times of strikes basically tell us that it's crazy, the amount of lightning. Lightning develops in 3 stages. Take a second to look at this. Starts in the cloud, charge separation. The updrafts and the downdrafts basically make it so that we have positive charges and negative charges separating, with the positive charges toward the tops and the negative charges towards the bottom. That's something that happens in the cumulonimbus cloud. Field generation means as this cloud comes over the surface of the Earth, this negative at the bottom of the cloud starts to induce a positive charge. It starts to pull all the positive charges in the soil and the earth towards it. They're attracted. Opposite charges attract. Once it gets time for discharge, what we'll see is that charge will start to lead forward, and we'll see a stepwise approach. We'll see a step leader come down, and then these positive streamers come up. And when the step line and the positive streamers hit, the discharge of all the plus going up and the minus going down occurs, and the cloud neutralizes. And that's what we call lightning. Check this out. What can be loosely described as an avalanche of electrons, that's the step leader, that's the return stroke. Let's pay attention to what's going on with the step leader. These things right here, coming down from the cloud, are looking for a place to go. It's a tortured route, takes a long time. This, when we look at it, that lightning bolt that we see is called the return stroke. The return stroke is basically takes about 1 microsecond to reach its peak of 30,000 amperes. That's the return stroke. And it produces 99% of the lightning and helps produce the thunder. It's what you and I would look at and call lightning. The step leaders, invisible. We hardly ever see them. The sound of thunder, though, when we hear thunder, you can imagine once that discharge occurs, what we get is explosive advances. That air gets heated to 54,000 degrees Fahrenheit in a fraction of a second. This heats the air so rapidly that it expands and compresses, forming a shock wave, just like you would see in fireworks or a sonic boom. That travels at roughly 750 miles an hour. The light travels a lot faster, something at like 186,000 miles per second. So it takes about 5 seconds for thunder to travel 1 mile. It takes approximately 1 mile for every 5 seconds. And that helps you kind of estimate how far the storm is away. But that rule of 5 seconds per mile is pretty good. Think about lightning. It's dangerous. And if you take a look at these statistics, there's 330 million people in the United States, 27 deaths, a lot of injuries basically occur every year. If you were going to be, what are the odds of you getting struck by that? Well, 1 in 1.2 million doesn't seem very much. in your lifetime, maybe 1 in 15,000. Okay, that starts to get a little higher. Odds that someone you know will be struck, let's say, one in, your little social group, maybe 1 in 1,500. If you look at the winning the lottery of 175 million, that odd of you being struck in a year by lightning is greater. It's more likely you'll hit by lightning than you would win the lottery. Crazy to think about. So in this video, I hope that you understood a little bit more about thunderstorms and their formation, lightning in its formation, and thunder in its formation. I'm going to invite you to look through our resources that we have. Inside of our assignment, these two websites will go through pretty much a lot more detail what I just talked about. But these videos are cool. This slow-mo one of lightning is really interesting. How thunderstorms form, how does lightning form, also useful videos that you can take. Answer the questions, either write an answer to the essential question or do the practice quiz on thunderstorms and lightning, and you'll be good to go. Hope you have a great week. Thanks for being persistent. I give you guys a lot of credit for keeping up with this. I appreciate your work, and I hope that you take care. Bye.